Hello, this is Mr. Collier, and today we're looking at the intersection between a line and a plane, or between two or three planes. Okay, so firstly, a line and a plane, there's three possibilities. The line could be parallel to the plane. Let me show you what that looks like. Here's a plane. The line could be up here parallel to it. Okay, it never touches it. The line could be parallel and contained in the plane, like it could be on the plane like that. Or it could intersect, and when that happens, it intersects at one point. Okay? So there's three possibilities. The first two are pretty easy to discover because the direction vector of the line is going to be the same as with the plane. Okay? Or you could take if you have the normal, you could dot product the normal with the direction vector of the line, and you get 0, and then you know they're perpendicular. Okay, so the third one is what we're interested in. When a line intersects a plane, there's one solution right here. And we're going to do an example like that. So here we got a line and a plane. I'm going to rewrite these a little bit differently. I'm going to rewrite this as 3x plus 2y plus kz equals 5. Oh, sorry. That's the unit vector k, so this is plus 1z equals 5, and over here I'm going to rewrite this as actually I'm going to rewrite this in parametric form. So this is x equals 1 plus lambda, y equals 6 minus lambda, and z equals negative 5 plus lambda. Okay, that's parametric form, and this represents any point on the line. Remember, the line looks like this, and it touches the plane at one point. So any point on the line is represented by these parametric equations, and we want to find this particular point, the point of intersection. So we can just substitute this point into the plane and solve for lambda. So we got 3 times 1 plus lambda plus 2 times 6 minus lambda plus negative 5 plus lambda equals 5. And then we're going to start solving for lambda. We got 3 plus 3 lambda plus 12 minus 2 lambda minus 5 plus lambda equals 5. And if you simplify that, you get 2 lambda equals negative 5, and lambda equals negative 5 over 2. Okay, so at this particular lambda, you get this point of intersection right here. So to get the point, you just substitute this back in. X equals 1 plus negative 5 over 2. Y equals 6 minus negative 5 over 2. And Z equals negative 5 plus negative 5 over 2. And when you add those together, you get like negative 1.5, 8.5, negative 7.5 is the point of intersection. Okay, next, if we have two planes, the following situation could occur. They could be parallel, okay, and never touch, right? Or they could actually be the same plane. That might be pretty obvious too. Both those would be pretty obvious. Or the two planes will intersect in a line. So that's maybe a bit harder to draw, but there could be another plane here and they intersect. Okay, something like that. So when they intersect, they'll intersect at a line if there's two of them. Alright, so here's the steps for solving this kind of problem. You can pause the video to read those if you like. Okay, so here we have two planes, and if they intersect and create a line, then if you cross product both normals, you'll get the line of intersection. Okay, so maybe I'll try to draw something like that. So there's the two planes. Alright, so the planes intersect here. So if you've got a normal here and a normal for this plane here, then if you cross product, you get a vector that is orthogonal to both of them, and it's going to be right there on the line of intersection. Yeah, it's not a very good diagram, but maybe you can find some better ones on the internet. If we cross product the two normals, we'll get the direction of that line. Okay, so let's do 1, 3, 1. Cross it with 2, -1, -1. And we'll do that lengthy procedure now. 1, 3, 1. I should always do these vectors. Okay, 2, -1, -1. Which equals a tiny determinant times I minus a determinant times j plus a determinant times k. And this is 3, 1, -1, -1, 1, 3, 2, -1, 1, 3, 2, -1. Let me just make sure this one's correct. This one is not correct. I messed up that one. Alright, so that was supposed to be 1, 2, 1, -1. Okay, so we get 3 times -1, -3 plus 1 is 4i. Let me just double check that. -3 plus 1 is -2. Oops. Okay, so that's -2i. And then we've got -1 minus 2 is -3. -3 is +3. And lastly, we've got -1 minus 6 is -7. Okay, so this is the direction vector for the line. And to get a point on the line, we're going to assume that this line touches the xy plane somewhere and takes a value of z equals 0. If that's not the case, you could take y equals 0 or x equals 0. Let's plug in z equals 0 and solve for x and y. Okay, so if z equals 0, we've got x plus 3y equals 5 and 2x minus y equals 1. I'll call this equation 1, equation 2. And I'm going to multiply equation 2 by 3. So I'll get 6x minus 3y equals 1. And I'll rewrite equation 1 down here. So we can obviously add these together. We get 7x equals 6, and that implies x equals 6/7. Actually, oops, this was supposed to be a 3, and then that makes this an 8. Sorry. So it's 8/7. So x is 8/7, and now let's get the y value using, I guess, this equation, sure. So 8/7 plus 3y equals 5. Multiply everything by 7. And we get 21y equals, subtract 8, I get 27. Y equals 27 out of 21, which is 9/7. Okay, so now we have a point on the line, which is 8/7, 9/7, 0. So we can write our answer for part A as the point 8/7, 9/7, 0 plus lambda times the direction vector is here. Okay, now find the angle between the two planes. You can use the equation cosine theta equals the dot product of the normals divided by the magnitude of the normals. The product of the magnitude of the normals. Okay, and then you can calculate theta that way. We're not going to do that right now. We're going to go on to the next problem. We're going to look at intersections of 3 planes. So these are some of the things that can happen. You can get 0 solutions, and sometimes 0 solutions looks a bit different. You could have 2 parallel planes and another plane that goes between them too, but there's no place where all 3 of them meet. You could have all 3 planes meet at one point, so it's a unique solution, we say sometimes. And infinite number of solutions is when you get a line at the intersection of the 3 planes. Okay, so here's some procedures that we're going to do to solve these linear equations or systems of linear equations. We're going to eliminate one of the variables. solve the two simultaneous equations for the two unknowns, and then we can figure out what's happening. These are the three different cases that happen when you get a point. So if you get a unique solution, that's like 1 point. That's when you intersect at 1 point. That, yeah, you get an equation like this at the end for z. And if the last equation, if you get something like 0 equals c, like 0 equals 6 or something, that's impossible, so there's no solution there. That would be like what happens in this picture. And if you get something like 0 equals 0 at the end, that means it's always true and you have like infinite number of solutions. Okay, so let's do an example. So here we have find the value of k for which the system of equations is consistent. Okay, so let's check that out. So consistent means it does have a solution. Alright, so here's k down here, and what we're going to do is we're going to start solving. Let's see. I'm going to probably add, well, I can add 1 and 2 together, and that eliminates the y. So let's do that first. 1 plus 2 gives us 8x minus 4z equals 12. And now we need to use another set of equations and eliminate the z. I'm going to do that for 2 or maybe 1 and 3. Looks a bit easier. So for equation 1, I'm going to multiply by 6. And I get 12x plus 6y plus 12z equals 24. And then write down equation 3 again. We get 4x, we got 6y, and 16z. So yeah, I multiply by 6 so that the y's would match, and then I'm going to subtract, and I'm going to subtract this way. So 4x minus 12 gives me negative 8x, and that's 0, and this is 4z equals k minus 24. Okay, alright, so we've got that, and I've also got this equation up here, which I'm going to call equation 4, and I'll write that down here. 8x minus 4z equals 12. And if we can solve this by just adding, and you see you get 0 equals, and you're going to get k minus 12. Okay, so let's go back now. If you get something at the end with 0 equals 0, then you get infinitely many solutions, and it's consistent. If you get like 0 equals some other number that's not 0, then it's inconsistent. So we want the case where we get 0 equals 0, so we want 0 here, so k must be equal to 12 to give us that 0 equals 0. Okay, so k equals 12 gives us a consistent system. If k is not equal to 12, you get an inconsistent system. For this particular value of k, find the general solution of the system. Okay, so that would be, yeah, that would be 12 here. We're going to use 12. And to get the general solution of the system, what we can do is this strategy right here. General solution can be found by setting z equals to t. So it's like picking a particular instance of t and solving x and y in terms of the parameter t. Okay, so let z equals t, where t is a real number. And then I'm going to take my equation 4 that I had from before. We have 8x minus 4t equals 12, and you solve this for x. You get half t plus 3 over 2. And so then I can take that and substitute it into another equation, like number 1. Yes? So we have 2 times x plus y plus 2t equals 4. And if you solve this for y, negative 3t plus 1 is what you get. So we got x, we got y, remember z equals t, so we got everything we need to write the equation. So we're going to have x is 3 over 2, 1, 0. And here for the direction vector, you're going to have half, negative 3 over 2. That's not half, that should be, oh, it is half, that's right. Half, negative 3, and 1. Okay, we have another system of equations, and we're asked firstly to find the values of k for which the system has a unique solution, or one solution, right? So we're going to have to solve it until we get down to like kz equals something. Alright, so we want those x's and y's to cancel, so we're going to solve till we get the x's and y's to cancel. I am going to, well, I'll call that 1, 2, 3 first of all. And I'm going to do 2 times 1. You can solve it differently, of course. 2 times 1 is 6x plus 4y minus 4z equals 2. And then I'm going to take equation 2, which is 2x minus 4y plus z equals 4, and the y's match. I'll add and get 8x minus 3z equals 6. Okay, perhaps I'll call that equation 4 if we need it later. And now I'm going to use these two equations to cancel out a y. So I'm going to do 4 times equation 3 gives me 4x plus 4y plus 4kz equals 4a. And then equation 2 is 2x minus 4y plus z equals 4. And I can add them together and cancel those y's. So you get 6x plus 4k plus 1z equals 4a plus 4. I'm going to call that equation 5. Alright, next, we're going to need to get the x's to cancel from equation 4 and 5. And this is 6 and 8, so the least common multiple is 24. So I'm going to have to take, let's see, 4 times equation 5 will give me 24x plus 16k plus 4z equals 16a plus 4. And 3 times 4 is 3 times 4 is 24x minus 9z equals 18. Is that right? 3 times 4? Yep, 18. Okay, so the x's match up. I am going to subtract. Alright, subtract, and the x's cancel here. I just subtract negative 9, so it's like adding 9. You get 16k plus 13z equals, so this is subtracting, so it's going to be, this is 16 right here. Subtract, you're going to get a 16a minus 2. Okay, so when you get down to this part, remember if this is 0 times z and this is a non-zero number, then you get inconsistent systems. So basically, any k not equal to negative 13 out of 16 would give you a unique solution. Okay, part B. For the value of k for which the system does not have a unique solution, find the value of a for which the system has infinitely many solutions. So they're talking about when k equals negative 13 out of 16. What you get then is you get 0z here equals 16a minus 2. Okay, so we get infinitely many solutions when this is equal to 0, then you get an infinite number of possibilities for z, and you get an infinite number of solutions. Okay, so this happens when Well, when a equals 2 out of 16 or 1/8. Okay, so when a is 1/8, then you get an infinite number of solutions to the system. State the set of values of k and a for which the system has no solutions. Okay, so no solutions happens when you've got k is equal to negative 13 out of 16, and when a is not 1 out of 8. Maybe you can say and in between, right? Okay, because when that happens, you get 0, z, and then equals, and then your 16a minus 2 is a number, let's call it k, or let's call it c, where c is not equal to 0, and then you get like an impossible situation, so there's no solution. Okay, next we're going to solve these three. We're going to solve them with the calculator and see what it looks like on the calculator and interpret the meaning. Okay, so actually let's go back to the main mode. So go to Polysmalt 2, simultaneous equation solver, and put it on 3 equations and 3 unknowns, which is what we have. Go to next, and just type in the coefficients. So we've got 1, 1, 2, 0. 2, negative 1, 1, negative 6, 3, 4, negative 1, and negative 6. Double check that all numbers are correct because it's easy to make a mistake. Click solve, and we get that solution, which means x, y, and z are negative 3, 1, 1. So in this case, we got the answer is negative 3, 1, 1. So they meet at 1 point, and we call it a consistent system. Okay, so then the next one, well, I'll just basically tell you what happens. If you put in the coefficients, you will get a message on the calculator that says no solution. Okay, so I'm not going to bother to go through that. No solution, and we call this inconsistent. Now for the last one, well, you probably guess it's going to be the other type. Let's see what it looks like on the calculator though. So we got 3, negative 1, negative 1, 1, 1, 2, 1, 4, 1, negative 5, negative 3, negative 7. Okay, double check that everything's correct, and when we go to solve, we get this. Okay, so when you get this is what happens when your point of intersection, or your intersection between the 3 planes, is a line. So let me just take a screenshot of that. Hang on 1 second. Let's do a little bit better job than that. So your answer here is your intersection is a line, and this is the equation of the line. It's going to be 6/7, 11/7, and 0, because there's nothing there, plus lambda times the direction vector is 1/7, negative 4/7, and this is just 1. Okay, so we have a line intersection, and we also call this consistent because there is a solution. Consistent. Okay, now in our last example, we've got a point A, and then we're going to reflect that over the plane and figure out where the new point is. Okay, so if we look at this carefully, when it reflects over, this is perpendicular, and we pretty much know the equation of this line. Okay, the equation of this line is, well, we need a point, which we have. Point is 1, 2, negative 1, and the direction vector is the normal to the plane, which is 3, negative 2, 1. So that's the equation of this line. So one way to solve this problem is to find this point Q. Alright, so any point on the line can be written as 1 plus 3 lambda, y equals 2 minus 2 lambda, z equals -1 plus lambda. That represents any point on a line. We want to find this point where it intersects the plane, so we can substitute it into the equation of the plane. 3 times 1 plus 3 lambda minus 2 times 2 minus 2 lambda plus -1 plus lambda should equal to 5. Solve that for lambda. You do the math, you get lambda equals half. So that means this point of intersection Q is going to have an x value of 1 plus 3 lambda, which is 1 plus 3 times half, and 2 minus 2 times half, and -1 plus a half. And simplify that, you get 5 over 2, 1, -half. So that's that point right there. Okay. And one way to solve this now is you get point A, then you get Q on the plane, and A prime over here. This is the midpoint, right? This is the midpoint. So we can use the midpoint formula. So in the midpoint formula to get the, actually for this A prime, let's call this point A, B, C, and then we'll solve for A, B, and C. So to get the x value here, you do A plus the x value over here, which is 1, divided by 2, and that gives you the midpoint, which we already know is 5 over 2. Okay, and then similarly we're going to have b plus 2 over 2 equals 1, and c minus 1 over 2 equals -half. Solving these little equations, you're going to get a equals 4, b equals 0, and c equals 0. So your point of intersection A prime, your reflected point A prime, is 4, 0, 0.